Okay, we're going to look at chapter 4 now, which is all about curve sketching. Curve sketching, a lot of this was done in advanced functions, but there are a couple little things that we could not do in advanced functions, and one of them was to determine where any function might reach a maximum or a minimum. Okay, and the other thing is where a function may start to curve from curving down to curving up. So for example, this one is curving this way and then all of a sudden starts to curve back this way. Or right here where it starts to curve this way, curving down, and then starts curving back up again. So the curvature starts changing. Okay, so I just drew this graph here out of, it includes a lot of interesting points. It's not any specific function. There might be some things here that might look familiar. It might look like a rational function, and it probably would represent a rational function. So if this is some function f of x, then we have some points of interest on here. So a, b, c, d, and e are all places where the function equals 0. Okay, so these are the zeros of the function from a to e. At g, we have a maximum. H, we have a maximum, local maximum. And I, we have a local minimum. At these points, at these points of these x values, the derivative of the function equals 0 because the slope of the tangent is 0 at those values. Okay, where this vertical asymptote is, the function is undefined. So it probably represents some rational function. This dotted line here represents an oblique asymptote, so a diagonal asymptote, not a horizontal one, but a diagonal one. Okay, and we'll look at how we get those. So some of the interesting points here are the maxes here and mins, and we've already seen a lesson on that, how to get the maximum. That's where the derivative equals 0. Okay, so if the derivative equals 0, it's not necessarily a maximum or minimum, but on a graph, if it's a continuous differentiable function, then at a max or a min, the derivative is 0. Okay, and there are tests for that. So here, where the function is curving up slightly, and then starting to curve down, we have a point in here somewhere where the curvature changes, and we would call that an inflection point. Okay, we would have another inflection point somewhere around here and around here. This function looks like it's probably a rational function where the denominator has a factor of x minus f. Okay, so the denominator might have some sort of factor of x minus f. So it might look something like this, where f of x equals some polynomial on the top and x minus f to some power even times something down here. Okay, because it's going to be undefined at x equal to f. Most likely this is going to be an even power because the asymptotes head in the same direction. Or not the asymptote, the function heads in the same direction around that asymptote. Okay, so a little summary of the information we've just talked about here is right here. The only part we haven't talked about is the oblique asymptote. Okay, so the function is 0 at a to e. It's undefined at f. Its derivative is 0 at g to I, g, h, and I. The limit as x goes to f is going to be undefined, but more descriptive would be negative infinity, because on both sides it goes to negative infinity. If it went up on one side and down on the other side, we'd look at the left side limit and the right side limit to describe it. And the left would go up to infinity, the right would go down to negative infinity if it went opposite directions there. The limit as x goes to infinity on this function would be infinity. And the limit as x goes to negative infinity on this function would be negative infinity. That helps describe the end behaviors. Okay, so the opposite end behaviors here. As x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to negative infinity on this one. Okay. In any function where you have an oblique asymptote, then we have that the numerator is 1 degree higher than the denominator. So for example, if you had f of x, okay, equal to a quadratic, x squared plus 2x minus 3 over x minus 4, well, if you divided that out, if you did the long division, you would get a linear function. And that would be, the linear function would be the oblique. Okay, so basically if you did this division, x minus 4 to x squared plus 2x minus 3, so you'd have x squared minus, sorry, not x squared, just x. So x times x is x squared minus 4x. Subtract, and you get 2 minus negative 4, which is 6x, minus 3. And you want to get rid of this 6x, so you're going to do plus 6. And you're going to get 6x minus 6 times 4 is going to be 24. And you have negative 3 minus negative 24, so plus 24, which is going to be 21, and you have a remainder of 21. Okay, so when you divide out this function, you get x plus 6 with a remainder of 21 as the answer. So this then becomes x plus 6, okay, so it equals x plus 6 plus 21 over x minus 4. Okay, so that function, when you divide it out, equals x plus 6 to 21 over x minus 4. As x gets large, so when we're talking about the oblique asymptote, we're talking about when x gets really large. Okay, so we're talking about when x is way out at the ends, not in the middle part here. It can do anything in the middle. It can go over and through the oblique asymptote or a horizontal asymptote. Just can't go through a vertical asymptote. Okay, otherwise it would not be a function. Okay, so as x gets really large, this piece becomes negligible. So when x is 1,000,000, 21 over 1,000,000 minus 4 is basically 0. And so the function just becomes x plus 6. Okay, so this oblique asymptote would be something like x plus 6 if that was the function here. Okay, so if that was the function. So anytime that the numerator is 1 degree higher than the denominator, when you divide it out, you will get a linear function on the top and a remainder, which will be not used in the oblique because it disappears basically like this as x gets large. And you'll have a linear, and that will be the oblique. If the numerator is more than 1 higher than the denominator, then the difference between the 2 degrees, when you divide them out, so say a quartic divided by a quadratic, would give you a quadratic. Okay? A quintic divided by a cubic would give you a quadratic. So the end behavior would be like a quadratic, depending on the leading coefficient. Okay? Or if you divide it out and the difference was 3, degree of 3, and you'd have a cubic as a result, and the end behavior would be like a cubic. But basically, if the top degree is higher than the bottom one, then it's more powerful than the bottom one. It takes over as x goes to infinity, and the end behaviors do go off to infinity or negative infinity if the top degree is higher. Okay, like this, they go off to infinity or negative infinity. They just go off in a linear fashion. Okay, so the end behavior here is like a linear. If the degree of the top and the bottom are the same, okay, so if you had a rational function where f of x equals 3x squared plus 2x minus 4 over, I don't know, x squared minus 5x plus 7, okay, when you look at this, when you divide this out, if you divided that, you would actually get 3 with the remainder. Okay, so that would equal 3 plus some remainder over that part there. Okay, so as x gets really large, these parts here become negligible. And basically the function is approximately 3x squared over x squared. And that equals 3. So when the numerator degree is the same as the denominator, you take the leading coefficients, divide them out, and that is your horizontal asymptote. Okay, so this one, for this function, the horizontal asymptote would be y equals 3. Because as x gets really large, the function approaches 3. Okay, if the denominator is higher degree than the numerator, so say you have f of x equals x squared plus 7x plus 3 over 3x cubed plus x squared minus 4. Well, basically, same sort of thing happens here. These ones become negligible. Okay, as x gets really large, this takes over and looks like x squared over 3x cubed, so approximately that, which is then 1 over 3x. And as x gets really large, this goes to 0. Okay, so when x goes really large, that tends to 0. And so for something where the denominator degree is higher than the numerator, you always have y equals 0 as a horizontal asymptote. Okay, so those are the cases for the horizontal asymptote. For the oblique asymptote, though, the numerator is 1 degree higher than the denominator.